So hope everyone can hear me right. So good morning, good afternoon, or good evening perspective to where are you? Thank you for joining us for this webinar organized by the Canadian Geotechnical Society Young Professional Committee. My name is Rajit Dayaratna and I am a geotechnical engineer at WSP Canada based in St. John's, Newfoundland. And I am serving the CGS YP committee as the knowledge lead and will moderate today's webinar along with Alex. CGS YP committee initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. We successfully conducted 4 webinars starting in January this year. So if you are interested in listening to past talkings, recordings are available on our YouTube channel, and I will post the link in the chat so you can go and check those. Before we get started, there are few housekeeping notes. To avoid any disturbance, audio and video access has been disabled. So if you have any questions, please use the chat option. The presentation will take about 40 to 45 minutes, and there will be a brief Q&A session at the end. If you have any questions for speaker, please type them in the chat, so we will take them as they appear during the Q&A session. Uh, it's my great pleasure to let you know that we have a well-experienced researcher and an engineer with us today, Dr. Ali Siamaki. I am sorry if I mispronounce your last name, Ali, from GKM Consultants. Ali holds a PhD in mining engineering and has spent the last few years focusing on geotechnical instrumentation and monitoring in the mining and infrastructure industries. His other area of expertise is digital technologies such as the Internet of Things on data science in the mining and infrastructure industries. He collaborates closely with mining and construction companies to provide near real-time data on their mines and tailing stability and condition. With over 25 published papers and a book chapter, he has a strong track record of research and has successfully managed numerous monitoring and instrumentation projects in open pit mines, dams, and tunnels. So without further ado, I would like to invite Ali to start his talk on geotechnical instrumentation and monitoring, fundamentals, case studies, and innovations. Over to you, Ali.
Thank you, Rajiv. Just please let me share my
Yeah.
screen with you.
Yes,
Please let me know if you have my screen.
I do have it. You can see.
Okay,
Perfect.
perfect. Thank you, Rajiv, for giving me the opportunity to speak today. As everyone knows, geotechnical instrumentation and monitoring is a key part of the mining and construction projects. And so today I'll talk about instruments, fundamentals, monitoring technologies, and we have many case studies to get a better understanding of these technologies. I'll talk about Internet of Things as well, their features, risks, challenges associated with implementing these technologies for geotechnical instrumentation. So thanks to Rajiv, he already introduced myself. I'm from GKM Consultants, which is a part of Keller company. GKM is established in 2007 and providing first-class monitoring solutions for mining infrastructure, dam projects all around Canada and also abroad. So we are with our clients from the first steps of designing instrumentation plan, then selecting right instruments, implementing them, installing, providing near real-time data, and also analyzing data. So today, quickly, I review geotechnical instruments, the technologies or the instrument sensors we have, and I try to put some case studies. The time's flying, so we have a short amount of time. So I try to go or review the concepts that we talk in each case study. Then we move to monitoring levels from manual monitoring to fully automated monitorings. We have it piling project. I'll review the monitoring plan for it. And then I'll talk about Internet of Things, since it's a major or main part of monitoring for mining and infrastructure projects. And at the end, I'll talk about a mining project that we try to select the right monitoring or IoT system for that. Geotechnical instruments will apply to wide range of projects, from dams, infrastructures, tunnels, subways, or waterway tunnels, to the transport roads, structures for structural health monitoring, and mining, environment, or the other parts of monitoring applications. But before moving forward and talking about instrumentation, let me talk about why we need to use instruments and monitoring for our projects, geotechnical projects. At first, we need instruments to characterize initial site conditions. So common parameters like poor water pressure, permeability of the soil, rock, slope stability are the things we need to record and monitor at first before starting any project. And also, instruments are used to verify design assumptions and to check that performance is as predicted. So instrument data from initial phase of a project may reveal the need to modify the design in later phases. Also, instruments are used to monitor the effect of construction. So I can say instruments data can help engineers determine how fast construction can proceed without the risk of failure. And also, the monitoring results can be used for quality control to make sure our operation is following the specification. It's a safe operation. There is no damage to surrounding structures or infrastructures. And also, it can be used to review the performance of the structure. For example, monitoring parameters such as leakage, poor water pressure, and deformation can provide an indication of the performance of a dam. Or monitoring loads on tiebacks or rock pools or movement within a slope can provide an indication of performance of a drainage system installed in a slope. We have different kind of instruments that can measure displacement, movement, pressure, load, vibration, and inclination, and also the many other parameters that I didn't mention here. But in general, we have four kind of instruments: vibrating wire sensors, the sensors that are based on vibrating wire technology; MEMS sensors, that I'll talk about it later; robotic total stations that automate surveying for us. I don't talk about robotic total stations because it would be a separate conversation, comprehensive conversation, and also the vibration monitoring. So let's start with vibrating wire instruments. A vibrating wire sensor couples an external physical parameter, for example, a strain or displacement or pressure, to the tension of a wire within the gauge. So because the tension of the wire is related to the wire's fundamental resonant frequency, every change in the wire frequency gives us a pulse that we can transfer or convert that to meaningful data. For example, when we have piezometers, as you can see here, the piezometers are used to measure water poor pressure. So any changes in water pressure can resonate the wire inside the piezometers, and the coils around the wire transform any vibration of the wire to the signals that we can get pressure. So based on vibrating wire technology, we can measure pressure, displacement, strain, and load. That here I have the most common sensors we use, as discussed, vibrating wire piezometers for measuring water poor pressure or water level inside the ground, total air pressure cells that are used to measure any load on embankment, or if you consider backfilling inside the backfilling stop. Also, NATM pressure cells are used on the tunnel wall if we are using an ATM method to measure applying load on shotcrete. Extensometers crack meters, and strain gauges are used to measure displacement and strain. So, for example, extensometers can measure any displacement along that extensometer while they have many different anchors, and every anchor movement will be compared to the head of the extensometer. We'll talk about it later. And load cells that I mentioned earlier can be used to measure applying load, tension loads on tiebacks or rock bolts. On the other side, we have microelectromechanical systems, MEMS sensors, that are based on accelerometers. So they can measure any dynamic loads like shock or vibration when we are talking about vibration monitoring, or they can measure static acceleration, which is used for inclinometers or tilt meters that measure inclination or any rotation. These MEMS sensors are very useful when we want to measure any the inclination or any the lateral movement of a structure. For example, tilt meters give us a point data, any radian deformation or movement of a structure, while inclinometers can be used to measure when you send down inclinometer inside one borehole. You can measure lateral movement of the borehole, or if you use in-place inclinometers, which is a chain of inclinometers connected to each other, you can automatically measure borehole movement during an operation. In addition to tilt meters, we have tilt laser distance meters that, in addition to tilt meter application like inclinometer movements, it can measure the distance between itself and the other surface. So it can be used inside tunnels for example, inside tunnels for measuring tunnel convergence. We generally review geotechnical instruments. So let's see applications in action. Here you can see subway construction that includes deep excavation, new tunnel, which are surrounded both by urban infrastructures and buildings. Therefore, we need monitoring systems to monitor ground settlement, lateral movement of the deep excavation, and also water pressure around the structure, and also the structural movement and behavior under construction to make sure our operation is under a safe manner. So here for deep excavation, you can see that we have piezometers around the area that like number 2 is a piezometers that can measure water pressure around the structure to see if water pressure is going up or down during operation. Also, we have extensometers that, as I said, extensometer can measure any movement along the extensometers. So if you consider we have 3 points here, movement of each point will be compared to the head of the extensometer to see how ground is settling. Inclinometers can measure lateral movement of deep excavation. So you know if the excavation is safe or the movements are going to exceed thresholds that need additional maintenance to maintain safe construction. Also, we have load cells under the tiebacks to measure tension and stress. And as I said, inclinometer probes that are connected to the piles measure support of excavation movements. Here we have Espadina-Eglinton tunnels in Toronto, Canada, that you can see the tiebacks and struts are monitored by strain gauge to monitor any the behavior of the struts under pressure. And also the load cells are used on tiebacks to measure the applying load on them. If we go to the next part, which is a tunnel, we can see same instruments are used in tunneling to measure, again, water pressure around the tunnel, or extensometers that are measuring settlement of the ground, that you can see here. They are measuring settlement of the ground and also soil layers. And if we use extensometer inside the tunnel, it can measure any movement around the tunnel wall, because when we are excavating, we have many different damage zones, and monitoring elastic and plastic behavior of these damage zones help us to I can say update or design and make sure tunnel and the surrounding structures are all in the safe zone. We also have crack meters that if there's a new project or if we have a liner inside the tunnel with some cracks, crack meters can measure movement of two sides of the crack or opening the crack and make sure the crack is not doing dangerous behavior. So earlier I mentioned about laser distance tilt meters. So when we have a construction, we have a new construction like an ATM tunnels, we usually use prisms to measure any convergence of the tunnel. And by using automated total stations, you can get data on predefined intervals. But this operation can be too expensive. By using tilt meters on the tunnel wall and also having them laser distance meters, you can measure any movement of each point and also its distance to the other surface of the tunnel. And by this measurement, you can get convergence data of the tunnel and make sure there is no dangerous movement inside the tunnel. But sometimes we have an existing tunnel right beside new construction, and we want to make sure that existing that construction doesn't have any effect on the existing tunnel. So you can install tilt meters or installing tilt meters on beams, making them tilt beams to measure any horizontal or vertical movement of the tunnel. Or if you install them on the ground on tracks, you can get any measurement of settlement, track settlements. So these sensors can be used to also monitor existing structures and make sure they're safe and there is no danger due to the other constructions. Here also we have extensometers that I mentioned. You can install them inside the tunnel. By installing them inside the tunnel, for example, this project, we have six anchors that recordings measure each anchor displacement compared to the head of the extensometer. So as you can see, for the deeper points as a 25 meter, you have the most settlement or movement compared to the head of the extensometer. And then, as also mentioned, inside the tunnel, existing tunnels or new tunnels, you may have some cracks and fractures on the tunnel liner that you need to use a strain gauge or crack meters to measure any movement of the tunnel surface. So let's talk about one of the projects we had as a case study. Earlier, we talked about the main purpose of instrumentation monitoring. Before talking about this project, let me review some of them. So, for example, monitoring plans help us to measure measures implemented for the safety of the public and infrastructure throughout the construction period and beyond. For example, here we have two tunnels under existing highway and also right beside another existing tunnel. Also, it can help us to evaluate project risk, both cost and schedule impacts, and also the soil and structure response to loading, unloading, followed by calibration of the design and parameters. And one of the most important parts is long-term stress settlement behavior of the tunnel or construction and its impact to structures within the project impact zone. So here we talk about RER project. As you can see here, we have existing tunnel under the highway, and there are two other tunnels will be constructed, actually was constructed under the highway by an ATM method. So here we have another view of the project, and you can see this tunneling. We've changed the ground stress regime and also apply new stresses to the highway, to the existing tunnel which may induce some settlements and movements. To reviewing the instruments we talked, in this project, we use horizontal SAAs or horizontal in-place inclinometers under the highway to measure any settlement that you can see the blue points, measure any settlement under the highway due to construction. We use single point extensometers on each part of the highway to measure any settlement, single point settlement compared to the head of the extensometers. So 11 SAAs, 7 inclinometers around the construction to measure lateral movement of the ground around the construction, and also 8 piezometers all around the construction, all around the tunnels to measure water pressure around it. In addition, we installed many vibration meters to measure both vibration from construction and also traffic and compare the results. If there's any settlement, compare the results to the traffic vibration and construction, make sure construction is under safe operation. As I said, I don't discuss AMTS here, but just for your information, for measuring ground settlement, we can also install some prisms on different part of the highway. And by using automate total stations, monitoring these points, reporting them on, for example, every 2 hours, every 5 hours, based on the intervals, to make sure construction doesn't have any effect on the surface or highway settlement. So far, we talked about instruments and their application. So here I'll discuss some of the different ways to get data from field to the office. We have split it to 4 levels: manual readings, standalone recorders, automate data acquisition system, and also remote data management. So at level 1, we have the collection of manual readings. So typically, manually read systems are the best suited for short time or infrequent data collection, where we have instruments in accessible area and we need data on regular basis. So, for example, piezometers or displacements. That a technician goes to the site and by connecting a readout unit to each instrument can read data at that specific time. So you don't have data between 2 readings. If you have many different instruments in close to each other, you can use manual switch type terminal box, as you can see in the photo, that you connected all instruments to this actually the terminal box, and you can read instruments by connecting the readout unit to each instrument. So, for example, here, this readout unit is used for only vibrating wire instruments. So we have other readout units for digital instruments as well. But at level 2, we still haven't gotten away from our field work, but we can be more efficient in how it's being completed. So at level 2, we start to use standalone data loggers. These units, which are able to schedule preferred data collection intervals, and you can return later to download data, and you can download all the recorded data based on those intervals. This method is a good one, but still you need to send someone to the site to measure data, and also you don't have data right after the measurement. That's why we need to move to steps 3 and 4. But here, let's review the technology for level 2. We have nodes or data loggers that have many different channels, but they can be used only for one technology. Like here, you have 5-channel vibrating wire node that all the vibrating wire sensors can be connected to it. And every time you need to send someone to download data between that interval. The next level is level 3, that here we can take data. Sorry, it went too fast. Here we take data, data loggers, and add some additional capabilities to make our lives a bit easier. So here you see we have many different instruments on site. So we connect them to multiplexers, and each multiplexers or different multiplexer will be connected to data loggers. At this level 3, we are using more complex systems where collected data, we are using more complex systems where collected data from multiple instruments can be accessed through a supervisor or master data logger. For example, if we use GeoNet wireless network, you can connect sensor to each GeoNet, and one master data logger will collect data from all GeoNets one, and you can record data or collect data from them. So the features is reading different sensor technologies at customized scan frequency. Also, it's flexible system that various topologies, it's expandable, and you can easily add more instruments to them. And these kind of data loggers can do complex calculations inside itself, and you can record, download the final results. Level 4 is about remote data management, but here the photo shows series of field technicians who are running instrument cables. I showed this picture to emphasize if we want to go with the methods like 1 to level 3, we need to run many different cables on site, and it's also expensive and time consuming to manage these cables. And if there is any damage to cable, you may lose some of the instruments. So that's why we need to move to remote monitoring technologies. In level 4, where the true ability of installed instruments can shine. Typically, data loggers will be used to communicate with instruments. You can, same as level 3, you can gather data from different kind of instruments inside one data loggers. Data loggers pass data, push data to cloud through SIM cards, Wi-Fi, or Ethernet. And you have layers for application layers that can present data and analyze data. I'll talk this one in the later section, which is Internet of the Things. But before that, let's talk about one of the projects to review all the instruments we use and the technologies. So here, in order to improve the understanding of drag loads, Ministry of Transportation Ontario was investigating in research to explore actual magnitude, distribution, and time dependency of drag loads on driven edge piles. For this reason, 3 piles within 14 pile were instrumented to measure drag loads. Just let me talk about drag loads a little bit. Settlement of soil after piles are driven applies additional loads to the pile. So this additional load is caused by friction or adhesion between this pile and soil. Down-drag load on pile is the sum of the negative shaft resistance along the length of the pile where the soil is moving downward relative to the pile. So getting better understanding of this applying load help us to probably review or spec and update or design to make sure piles are working well in the field and action. So the instrumentation program for this project includes monitoring 4 parameters: total deformation of pile, localized. Sorry, I don't know why the slides are moving so fast. Localized strain on the pile, settlement of the soil surrounding the piles, and also pore water pressure in the vicinity of the piles. So as we discussed many times, for pore water pressure, we use piezometers to measure water pressure. For deformation of the pile, we use single point extensometer. So as we discussed, extensometers have different anchors, and moving of each anchor can be compared to the head of the anchor to measure deformation and also settlement. But here we are talking about piles. We installed a small diameter steel pipe inside the edge pipe and inserted a single point extensometer, which it has a hydraulic bladder or anchor at the bottom. And you can see the head of the extensometer here, and it can measure any deformation up to 100 millimeter. For measuring soil settlement or deformation of soil around piles, we installed two extensometers in this project. And here you can see extensometer has different anchors. So this is multi-point extensometers. And we have three heads here, which are connected to vibrating wire transducer that can read up to 200 millimeter movement of the anchors. And the other part, localized strain on the piles. And therefore, forces on the pile can be measured through strain gauges that you see here. We installed strain gauges on 2x2 on each side of the piles. And the recorded data from them will be collected via data logger. So in this case, you can see how the level 3 monitoring can help us to have a data logger, collect data from different kind of instruments, and by using level 4, we can push data to the cloud and analyzing them. We talk about level 4 many times, but these days we call level 4 as Internet of Things. Having understanding of Internet of Things characteristics help us to design a better monitoring plans and monitoring solutions for geotechnical projects. Just quickly review the features. It's dynamic. You can add instruments later or during the project to these systems. You can have instruments from different manufacturers, different technologies inside one system. And also each sensor has its own ID. So you can check if there's a problem with sensor, if you're missing the sensor, or if it's malfunction. There's a malfunction. To reviewing IoT architecture, it has 4 levels, from sensor levels, that the sensors we discussed, to node level, which is data loggers that will be connected to sensors. They have 3 components: data logger itself, radio module to communicate with edge level, and also battery. Edge level remotely and wirelessly will communicate with all the nodes within the system to collect data from them and push data through cellular modem or satellite modem to the cloud. And on cloud, we have app layer, application and management layer, which you can securely record data and define some graphs, reports, charts, and thresholds to get notification if you are exceeding one of the thresholds. So node layer is working to fill the gap between sensor and the edge layer. It's good to know we have many different node technologies as star networks or mesh networks. When we are talking about star networks, it means that there is a direct communication, there is a direct line of sight between node and edge layer, which is gateway. So node can collect data, push data to edge, which is gateway. But if we have a hard topography, we have many different blind spots. We can there is no direct line of sight between node and gateway. We can use mesh networks. In mesh networks, each node will communicate with the adjacent node, push data to the next one. And once we have direct line of sight between node and gateway. Gateway can receive all data from nodes connected together. We reviewed IoT characteristics and architecture, but can we use same IoT system for different monitoring projects, or if we have a system, can we be confident that we have reliable data? So it's good to know we have many different risks associated with IoT systems. Like there's a risk with data collection from monitoring system, that data may not be accurate or reliable, or there's a risk with analyzing data, that misunderstanding or misinterpretation of data lead us to the incorrect or wrong decisions. And we should know IoT system needs maintenance. And if we don't follow maintenance, there may be damage to the system in the near future, some false alarms. And finally, if not chosen properly, monitoring system may be costly or over budget, which could affect the overall cost of the project. And the other thing I should quickly review this part, because it's very important. We hear that many aspects of project ask for real-time monitoring, but in reality, data are not real-time, because when you record data, data logger has its own processing time to process data, do some calculations, and then push data through the cloud. So there is a delay in network latency, and also sometimes we need human factors, like a person should review data and release data. So for all of them, we never have data in near real time, but we have data in real time. For example, if we have 30 sensors on site and we are recording data, maybe in an hour or half an hour, based on the volume of data, we can show data on cloud or platform. So to reviewing all the things we talk on Internet of Things and level 4, we have a mining project here, mining project in Canada, that we have about 400 piezometers, about 2,000 temperature points, 20 inclinometers for monitoring lateral movement or slope movement around the pit and tailing dams, and also dozen of TDR cables that are used to monitor lateral movement of the actually monitoring the slope behavior. We talk about instruments on site. We have many different instruments, but do we need to monitor all of them in near real time? I mean, do we need to use layer 4 for all of them? Categorizing sensors as background, regular, and critical sensor in IoT system help us to prioritize their importance in monitoring and managing data. So this approach helps us to reduce investment costs, capital costs, and also reduce maintenance over the project, and it helps us to prioritize our maintenance systems. So generally, I can say regular sensors provide ongoing feedback on the system performance, while background sensors provide additional information on operating environment, allowing for more comprehensive understanding of the system behavior. And critical sensors are the sensors we need data on real-time basis. Here you can see the topography of the mine. As I said, we have many different instruments, and monitoring them would be difficult. So we need to use data loggers that, like level 3, we have multiplexers. We connect sensors in each cluster to each multiplexer, and each multiplexer will be connected to a master data logger. So master data loggers collect data from different parts or different clusters and communicate them to edge layer to promote our level 3 monitoring system to level 4 by edge layer. And the edge layer can push data to the network. So as you can see here, we have about, I think, 75 data loggers on site. And the distance between instruments and data logger varies from 100 meter to 500 meter. And the distance between data loggers can be up to 1 kilometer, 2 kilometer in this project. And here you have architecture of the project. I mean, data logging system that you can see multiplexers are connecting as a bridge between sensors and data logger. So they can be wired from multiplexer to data logger, or each multiplexer can communicate based on radio network with data logger. And all data loggers push data to the base station or edge layer via radio. And finally, edge layer push data through Ethernet or Wi-Fi to the network. Thank you for your attention. I try to be fast to cover different aspects of geotechnical monitoring and give you an idea what kind of instruments do we have, why we need monitor structures, and what kind of data we can get from monitoring. Also, I try to review technologies for monitoring to make sure we are aware of different technologies and can optimize our monitoring plans by choosing the right instruments. I would be happy to answer any questions.
Thank you so much, Ali, for your interesting presentation.